Now for something a little different. These are notes I prepared in 2008 on the Centennial of the Axiom of Choice. So we'll go through this kind of with an eye towards applications of the Axiom of Choice in the construction of a non-measurable set, a topic covered in our Real Analysis 1 class. So here's an image of Ernst Zermelo, the star of this presentation. And the year I made these notes out, 2008, marked the 100th anniversary of Zermelo's first statement of the currently accepted axioms of set theory, including the axiom of choice. He presented two papers in 1908. One, a new proof of the possibility of a well-ordering, and a second one, Investigations in the Foundations of Set Theory, Part 1. Translations of these can be found in a book, we'll refer to this a few times, from Frege to Gödel, a source book in mathematical logic, 1879 to 1931. It's Harvard University Press. It's fairly old. It's still in print in paperback, but it includes English translations of these two works. And what Zermelo is up to in these two papers, the first one at least, is to address criticisms of his 1904 paper, Proof that Every Set Can Be Well Ordered. This also occurs in that Frege to Gödel book. In the 1904 paper, Zermelo uses the axiom of choice to prove that every set can be well ordered. And we'll explain some of this terminology here shortly. The math community, they didn't react so well. So Zermelo publishes this paper in response to the criticisms. In the second of those papers, Zermelo presents the first axiomatic set theory. So he lays out 7 axioms. We'll state them here in a second. This is about the same time Russell's paradox has surfaced. So set theory's undergoing a bit of turmoil. It's worded here. The foundations of set theory were coming into question. You likely run across Russell's paradox and maybe in math reasoning, possibly in senior level analysis, when you have to introduce some ideas from set theory. Part of Zermelo's paper involves constructions of sets and the axiomatic existence of certain sets. The problems encountered in Russell's paradox is you can't just go around willy-nilly defining sets. There has to be a protocol laid out that gives the existence of sets, and that's what Zermelo is up to in laying out his axiomatic approach to set theory. In some sense, sets just can't be quote-unquote too big. Russell, about the same time, introduces something he called his theory of types, also to address this problem that arises in not having clear definitions about when, or clear axioms, about when you can and cannot construct certain sets. Zermelo seems to be the first to see the existence of an infinite set. It needs to be taken as an axiom as well, quoting one of those references. And the final axiom we'll state is the existence of an infinite set. So Zermelo states these 7 axioms, paraphrasing a bit from the original. Axiom of extensionality: if M is a subset of N and N is a subset of M, then set M equals set N. Axiom of elementary sets. Okay, so this is the first time in the list, it's the first time he's bringing in the axiomatic existence of certain sets. There exists a null set, an empty set, that contains no elements. For any object A in the universal set, the set consisting of that element A exists. If A and B are in the universal set, then the set consisting of A and B exists. So to start with, we didn't go through all the details on this, CA and elementary set theory class. We'll reference a book by Herbacek and Yak that gives excellent introduction. That's probably where I got these statements, in fact. To have a conversation about set theory, we need to have an agreement on what the universal set is, the universal set of discourse, I think it's also called. But we have some big umbrella set under which we're discussing the existence of other sets. So in this universal set, if A is an object in that universal set, then the set consisting of A exists. The set consisting of element A and element B exist as well, where A and B are in the universal set. So this gives us existence of certain elementary sets. It's an axiom of existence, exists, exists, exists. So this is a way you know that certain sets exist. And you can see there's an angle towards avoiding just maybe allowing anything in that I could imagine as a particular set. And all this is done under the umbrella of the universal set as well. The axiom of separation, this is more familiar to you than you think, states for proposition P of x with a truth value for all x and m, some subset of the universal set, has a subset m sub p containing as elements those elements x of m for which P of x is true. The axiom of separation. All right, what this is when you see something along the lines of the set of all elements such that, and then some condition is given. For example, we might have the set of all x an integer such that x is congruent to 0 mod 2. So you're conditioning, you're adding this condition, this proposition, P of x is 0 mod 2 in that case. You're adding this proposition, and every integer has a truth value. It's either 0 mod 2 or it's not. So that's the meaning that a truth value can be assigned to all the elements in set M. And then we're taking those elements that are even. We're taking the even integers by taking all elements of the integers such that, say, x is congruent to 0 mod 2. So it's this such that part you commonly see in statements of sets. That's the axiom of separation. So if you can introduce a proposition, a meaningful proposition, that is, truth values can be determined, true or false, then we can define sets using this conditioning idea. The axiom of the power set, yet again, an axiom that exists, an axiom that claims the existence of certain sets. For every set T, there corresponds another set, P of T, the power set of T, that contains as elements precisely all subsets of set T. So if a set T exists, then the power set of that set exists. You may encounter this, if you've encountered set theory at all in the past, in the rather interesting discussion of cardinalities. You see that the cardinality of the power set is always strictly greater than the cardinality of the set itself. Finite sets, no problem. If a set has n elements, the power set has 2 to the n elements, a common thing you'd prove in math reasoning. But the same holds for infinite sets as well. So if I have some infinite set and I take the power set of that, I get a set that's strictly bigger in cardinality. So this leads to the concept of levels of infinity. There's bigger infinities and smaller infinities in some sense. That's also the realm of set theory and cardinal numbers, but that's not where we're headed. The axiom of union. Okay, maybe a comment here. In set theory, very strictly speaking, the only thing there is sets. Everything is a set. Elements of sets are sets. Everything is a set. The axiom of union states, for every set T, there corresponds another set, union T, the union of T, that contains as elements precisely all elements of the elements of T. Everything is a set. So for example, if T were the set A, B, C, then A, B, and C themselves are elements of T and are themselves sets. Everything is a set. Then the union of T would be A union B union C. Okay, so it's an odd way of saying it, but if a certain collection of sets, a set of sets, is known to exist, then we can take the union of those sets. So, axiom of union, reasonable thing. The axiom of choice, I'll put this one in quotes, we'll state this a couple of different ways. Here the statement is, if T is a set whose elements all are sets that are different from the empty set, and all these sets are mutually disjoint, its union, union of T, includes at least one subset, S sub 1, having one and only one element in common with each element of T. All right. We'll illustrate that somewhat with examples. If I look back up here, they've used the T and the union of the T very explicitly. What that would mean up here is, to get it in context, we need A, B, and C to be non-empty sets, and we need them to be pairwise disjoint. That's the setting of the axiom of choice. The axiom of choice then guarantees the existence of a set S sub 1, which in this case would contain three elements: some element of set A, some element of set B, and some element of set C. So that's what the S1 set is. We'll introduce something called a choice function before we're done, but right now the idea is you're choosing an element of A, you're choosing an element of B, and you're choosing an element of C in the creation of this set S sub 1. That's the reason it's called the axiom of choice. But we'll deal with that verbiage again here shortly. But that seems like a fairly innocuous thing to claim. It has some surprising implications. It has some useful applications as well. And a final axiom, remember we commented above that Zermelo is the first one to say we need to axiomatize the existence of an infinite set. This is happening. Zermelo's doing his work in 1908. Set theory it's probably been around at that time, 50 or 60 years. Now, axiomatic set theory is just being born in the early 1900s. So here's how Zermelo claims the existence of an infinite set. There exists at least one set Z that contains the null set as an element, and that for any A in this set Z, the set consisting of A is in set Z. Okay. It's not immediately obvious that implies the existence of an infinite set, but think of it like this. Z would have to contain the empty set. Now think of A as an element of Z, then I think of A as the empty set. Then the set consisting of the empty set must be in set Z. The set consisting of the empty set is in set Z. Well, since the set consisting of the empty set is in set Z, think of that as A, an element of set Z. Then the set consisting of that must be in Z as well. The set consisting of the empty set. And the set consisting of that must be in Z, and so forth. So we get this chain of sets that must be in set Z. Set Z is called an inductive set, and this is commonly the way the natural numbers are axiomatically defined, something along the lines of this, a particular inductive set. But since ... we could continue this process of taking sets of the previous one, set consisting of the previous set, then we get an infinite chain here. So that's the reason it's called the axiom of infinity. Here's another statement of the axiom of choice from Yeck's 1973 book. We'll look at those books on the last page and talk a little bitty bit about them. But Yak states the axiom of choice as follows. For every family, calligraphy F, of non-empty sets, there is a function f such that f of s is an element of s for each set s in that family. And this function lowercase f is called a choice function. Okay, here's what that means. So I've got a family of non-empty sets. We've lost the statement of disjointness that we had in the previous Zermelo statement of the axiom of choice. But we've got a collection of non-empty sets, and the f function picks an element of that set. F of s is an element of set s. So from any one of the sets, the choice function reaches in and chooses, kind of like a representative of that set, chooses an element of that set. We could use the choice function then to create the set like S sub 1 that was discussed above. To get the set S sub 1, I'd have to worry about disjointness to be quite technical about it. But this is what a choice function is, and this is an alternative way to state the axiom of choice. Some object to the axiom of choice. It's very non-constructive. Doesn't tell you how to choose these elements. And it's pretty easy to illustrate that leaves a degree of ambiguity of pragmatically how you might sit down and actually pick elements of these sets. Suppose we take as a family of sets, say sets X and Y, make them non-empty, and disjoint, maybe to jive with Zermelo's ideas. So these are just arbitrary sets of real numbers, well, non-empty and disjoint. How would you choose an element of set X? And can you describe constructively how you choose an element of set X? Greatest element, the largest element, maybe an absolute value, might not have a largest element. The one of minimal absolute value might not have one of minimal absolute value. The one in the middle, that's probably not going to make any sense. So actually describing how these elements are chosen, when I know very little about these sets X and Y, you can see how that, I suppose potentially objectionable. It's not a constructive way. It simply guarantees the fact that you can pick an element of set X and an element of set Y. Doesn't tell you how. It merely claims the existence of a set that contains an element of set X and an element of set Y. So as with most of those other axioms that Zermelo laid out, it's an axiom claiming the existence of a particular set. Now there's some weird implications of the axiom of choice. And I've usually given this presentation as something supplemental to a Real Analysis 1 class on measure theory. The axiom of choice can be used to construct a, in the sense of Lebesgue, a non-measurable set. A related result is the Bona-Tarsky paradox. I refer you to other sources for some more details on this, but the Bona-Tarsky paradox uses the axiom of choice to, get this, decompose a sphere into 5 pieces. So we take a sphere under some weird application of the axiom of choice, we partition that sphere into 5 pieces. So we've broken the sphere into 5 pieces. It's a partition. So every point that was in the original sphere is in one of those 5 pieces. When I take those 5 pieces and rigidly glue them back together, we get the original sphere. But it's possible to take 2 of those pieces through rigid rotations, rigid translations, take 2 of those pieces, glue them together, and get a copy of the whole sphere. The other 3 pieces, you can take those, rigidly rotate, translate, glue them together, and get a second copy of the sphere. So what you've done is you've taken a sphere of radius 1, you've broken it into pieces rigidly, you didn't stretch anything. That's what I mean by rigid rotations, rigid translations. You didn't stretch it at all. You simply took the sphere, you broke it into 5 pieces, you glued 3 of the pieces together, got a sphere, you glued the other 2 pieces together, got a sphere. That's the same volume as the original sphere. So it seems you doubled the volume out of nothing. All right, physics doesn't work like that. Measure theory does on certain really bad sets. And those bad sets are known to exist by the axiom of choice. Don't read that there's a problem here with the axiom of choice. This is pretty wild stuff, but it's not a problem. One would interpret this in a measure theory class as, yeah, we don't have additivity. So when I add up whatever the weights and the volumes, if that's not really meaningful, but if I could put some concept of volume on these 5 pieces, I add the volume of the 5 pieces, it doesn't add up right. It should add up to the volume of the sphere, and it doesn't, because we've created 2 spheres out of 1 sphere, like a magic trick. It ain't a magic trick, it's the axiom of choice. Dealing with that in the Bona Tarsky paradox requires access to the 3rd dimension and some rotations. But you do the same thing in measure theory. You construct a non-measurable set, and you can use that to go through and do a similar type thing of doubling length. You double the length through some rigid transformations with non-measurable sets. It's because there's bad sets out there on which, say, Lebesgue measure doesn't work. There's non-measurable sets. A sort of a 3-dimensional analog of Lebesgue measure doesn't work. So you're violating additivity with these particular things here. And you took the axiom of choice and did that. So this is an implication of the axiom of choice to which some folks have objections. I'm no set theorist. I've known a set theorist or 2 in my day, but not many of them. I get the impression the objection to the axiom of choice is not so much that it isn't constructive, and I use the word construct down here. Maybe that should be in quotes, because the construction is based on the axiom of choice, and it doesn't tell you how to construct. It simply tells you of the existence of such sets. But I think the real objection to this is these ideas of non-measurable sets in the Bona-Tarsky paradox. I think that's their objection to the axiom of choice, not this constructive stuff, just my opinion. But don't read physics into this. This ain't physics, it's pure math. And it's a common property of Lebesgue measure set. There exist non-measurable sets. Stay away from them if you want to set up Lebesgue integration. So that's an implication, and a weird implication of the axiom of choice. There's also some very useful implications of the axiom of choice. Here's 3 quote-unquote principles equivalent to the axiom of choice. The well-ordering principle: every set can be well-ordered, sometimes called Zermelo's theorem. We'll talk about what these words mean down below. Zorn's lemma: pretty fair chance you've heard of Zorn's lemma. Let P, comma, let me refer to this verbally as less than, be a non-empty, partially ordered set, and let every chain in P have an upper bound. Then P has a maximal element. Zorn's lemma. We'll define that terminology down below, but after that weird Bona-Tarsky stuff, I feel motivated to defend the axiom of choice. This equivalent to the axiom of choice, Zorn's lemma, you're probably going to see Zorn's lemma in a senior level math curriculum. You would see it maybe in a setting where you show maybe senior level algebra. Every field has an algebraic closure that requires Zorn's lemma. It's arguably hidden underneath sophomore linear algebra, where you talk about vector spaces and bases of vector spaces. How do you know every vector space has a basis? Zorn's lemma is how you know. Probably nothing you words you don't utter in a sophomore linear algebra class. But you don't know that a vector space necessarily has a basis without Zorn's lemma. So Zorn's lemma gives the existence of some nice things, bases of vector spaces, algebraic closures of fields. I'm sure there's plenty more, but that's the two I'm aware of. And so likely you've encountered this maybe in a senior level class. So these are useful things that we need the axiom of choice for. And it's got that weird implication of the Bona-Tarsky paradox and the existence of non-measurable sets. I say, small price to pay. That's just the way measure behaves. And the maximal principle 2, Tucky's lemma. If calligraphy F is a non-empty family of sets, if calligraphy F has finite character to be defined below, then calligraphy F has a maximal element, maximal with respect to set inclusion. Now these ideas of partial orderings and well orderings and what finite character means often involve subset inclusion as the partial ordering, for example. So let's go through some of the definitions about what these words mean. Again, from the Herbacek and Yek book, a set R is a binary relation on set A if all elements of R are ordered pairs of elements of A. The pairs is the reason it's called binary. We'll denote the fact that the ordered pair AB is an element of R as this, and we'll read this, A is related to B. A binary relation on A, which is reflexive, that is, A is related to A for all A. Anti-symmetric, that is, for A related to B and B related to A, we have A equals B, reminds me of less than or equal to on numbers. And transitive, A, B, and C in set A, where A is related to B and B is related to C, implies A is related to C. This reflexive, anti-symmetric, transitive sounds a little familiar. You've probably dealt with reflexive, symmetric, and transitive before. That was a binary, that was an equivalence relation. So this is a little bit different from that because of the anti-symmetric thing. But a binary relation R in a set A, which is reflexive, anti-symmetric, and transitive, is said to be a partial ordering of A. So that's what a partial ordering is. We'll denote it with the usual less than or equal to, in this conversation at least. It's called a partial ordering because, and all it is a collection of ordered pairs. Well, some of them ordered pairs might be there and some of them might not. Then we may have a situation where we don't have A is less than or equal to B or B is less than or equal to A. Neither of those may hold. Well, in that case, A and B are not comparable. If, definition here is if A and B in set A satisfy either A is less than or equal to B or B is less than or equal to A, then A and B are said to be comparable. Okay, that's why it's called a partial ordering, because there may be A and B that are not comparable in the set. And if I think of this less than or equal to in terms of a subset inclusion, that's a good place to go for examples of partial orderings. An ordering is called a total ordering if any two elements of A are comparable. So not a partial ordering, but a total ordering. Let's consider subset inclusion. This is a very classic example of a partial ordering. Take a subset inclusion as a partial ordering, say, on the power set of the reals. It's partial ordering because there's some subset of the reals that aren't comparable under subset inclusion. Take the interval from 1 to 3 and the interval from 1 to 2. Definitely in the power set of the reals, but neither is a subset of the other. Okay, those two elements of the power set of the reals are not comparable under subset inclusion. And you can check quickly that subset inclusion is reflexive, anti-symmetric, and transitive. So there's actually the most common example of a partial ordering. If we look at just the usual less than or equal to stuff, say on the real numbers, that's total ordering. So regular less than or equal to, the ordering on the real numbers is a field, more of that shortly, is an example of a total ordering set. Total ordering denoted with this little bent less than, curvy less than. Total ordering of a set A is a well ordering if every non-empty subset of A has a least element with respect to that total ordering. Least elements. Then we could observe by example that if we take the regular less than or equal to on the natural numbers, that's a well-ordered set. Because you give me any non-empty subset of the natural numbers, there's a smallest natural number in that set. Natural numbers being 1, 2, 3. Some people include 0. There's a smallest natural number in any subset of the natural numbers. Doesn't work on the integers with this. Right? I could take the integers. Well, there is no least integer. I can just choose larger and larger negative values to get lesser and lesser integers. So it's important I use the natural numbers in this conversation. Similarly, less than or equal to is not a well ordering on the reals. Take this set A as described above. There's not a least element of set A with respect to the usual ordering of the real numbers. For the same reason, there's not a smallest positive real number. Right? You give me a candidate positive real number, I multiply it by a half, and I get a smaller positive real number. So not a well ordering on the reals, a well ordering on the natural numbers. The well ordering principle says there is a well ordering of every set. Okay. Usual less than or equal to isn't a well ordering of the reals. But according to the well ordering principle, out there somewhere, there is a well ordering of the reals. It's just not that ordering that you're used to using. So a little comment about that in the next note. The term well ordering is being used somewhat differently from the idea of a less than or equal to type ordering of field elements. Maybe you've heard there's no ordering of the complex numbers. Maybe you should put that in quotes as well. Well, every set can be well ordered, but the term ordering in that statement is being used differently. What this means is there's no way to define a less than or equal to on the complex numbers in such a way that the usual ordering on R comes out as a subordering. So there's the term ordering simply means something different there. We're talking about an ordered field, and that's what the real numbers are. Real numbers are a complete ordered field. In fact, they are the complete ordered field because any two complete ordered fields are isomorphic. But that's a different concept of ordering. That is a less than or equal to that you're used to dealing with. And you'll define that in probably analysis 1, senior level analysis 1. It requires a property of it's called the Law of Trichotomy. You partition the reals into a set of positive, well, you partition a field into a set of things which are positive, and everything in the field is either positive or negative, or it's 0, the additive identity in that field. That's a different thing. The same words are used, but that use of order, in terms of ordering of a field, that's not the same as what we're talking about here in terms of well orderings. So sorry, the words are similar, but different ideas. Though I can use this field ordering stuff to give some examples of some of these other things, but different stuff. We mentioned chains above. Let's see what we're talking about in terms of chains as a definition. A subset C of a partially ordered set, P with this partial ordering is a chain in P if C is totally ordered by the partial ordering. So it's some subset on which you take any two elements of C, one is less than the other, or the other is less than the one of those two things open. They're comparable. So any two elements of C are comparable under the partial ordering. That's what a chain is. U in the partially ordered set P is an upper bound of a chain if anything in the chain is less than U with respect to that partial ordering. Element A in P is a maximal element if this occurs. All right. A is maximal. I got a number of ways to choose my verbiage. How about this? A is a maximal element of P if there's nothing bigger than A in P. So that's basically what the highlighted stuff says. Maximal doesn't, I want to say it doesn't mean it's the maximum element, but there's nothing bigger. There may be some things that are not comparable to A. And then I don't have a sense of bigger and lesser when they're not even comparable. So maximal elements are stated in terms of this, there's nothing bigger. That's a common use of the term maximal as well. Maximal Principle 1, Zorn's lemma, states that a non-empty partially ordered set P for which every chain in P has an upper bound has a maximal element. You use Zorn's lemma to prove vector spaces have bases. You do so by using an idea of sets of vectors that are linearly independent. So you take sets of vectors that are linearly independent and you order them by subset inclusion. That sets up a situation where you can apply Zorn's lemma. The existence of this maximal element, the existence of that maximal element is the basis for the vector space when sufficiently couched in the language of set theory. So that's how Zorn's lemma, or equivalently, the axiom of choice, is used to establish the existence of a basis for vector space. And similarly, this idea of partially ordered sets and upper bounds, that's the same application to show that, for example, every field has an algebraic closure. Finite character was mentioned. Let's just get that on a table as to what the meaning of that was. This was in the Maximal Principle, Part 2. Let calligraphy F be a family of sets. We say that that family has finite character if for each set X, X is in this family if and only if every finite subset of X also belongs to that family. So it's a kind of closure on the family of sets. Anything in the set, all finite subsets of that set must also belong to calligraphy F. It doesn't require calligraphy F to consist only of finite sets, of course, but when it has a set in it, then all finite subsets of that set must also be in the family. That's finite character. The Maximal Principle 2, Tucky's lemma, states that every non-empty family of sets of finite character has a maximal element, maximal with respect to subset inclusion. So I'm in no position to prove that those three principles, as we call them, are equivalent to the axiom of choice. But you know, the maximal principles 1 and 2, they sound a little bit alike. So that's not a surprising claim that they're logically equivalent. My references for this are the following 4 books. An excellent introduction to set theory is given by Herbacek and Yek. Yek is a big name in set theory. This is a very readable book at the junior or senior level. If you've had math reasoning, you can read through this book. Set theory can be a touch, in my opinion, on the nightmarish side. with a level of detail, but it's good, clean, logical stuff. And this is a readable book, a readable undergraduate book. It appears quite old. There's a third edition out that they've added a bit more material to. I think they've added another chapter on, what's it called, nets. I forget. They've added a new chapter to the new edition. There's a newer edition in 1984 of this book out, but it's an excellent book. Yak also has written, it's almost like a monograph called The Axiom of Choice, also fairly dated. This is still in print as a Dover book, which means it's not very expensive. It reads a lot like a monograph, though. It's rather crudely typeset, but it is still in print and floating around out there, dealing specifically just with the axiom of choice. We mentioned this book, From Frege to Gödel, a source book in mathematical logic. So it contains translations into English of the three of the papers that we mentioned here. I think they were all three by Zermelo. So Zermelo is the star of this presentation because he's the one that introduces the axiom of choice. But it's got works by Russell as well in it, for example. And there's a book called Labyrinth of Thought, A History of Set Theory and its role in modern mathematics, published in 1999. This is still in print as well, and this is out in paperback, which is a touch more affordable. It's an encyclopedic history of set theory. One of these days I'm going to read it. Now, about 2/3 of the way through it, and I kind of moved on to something else. But a very thorough history of set theory. And there's our brief introduction to the axiom of choice, some notes I have left over from 2008 when it was the Centennial celebration of the axiom of choice. Have a nice day. We'll move on to some other things now. The next place to go in my mind with this is let's create a non-measurable set. Let's use the axiom of choice to construct a non-measurable set. And that should bother you a little bit. Construct's probably not the right word to use. We'll show the existence of a non-measurable set. Check you later.